Okay, let's continue our discussion on attributed translation grammar, and we are still using the Decaf grammar in this particular subtopic. So in this subtopic, we will be talking about translating control structures. What are control structures? Control structures are structures such as if, else, while, and for. And in topic 2, when we were discussing translation from Java programming language into forms such as atoms and assembly language, we have discussed about this. So for example, if we have an input like this, the previous way that we translated this statement is we need to remember the structure. So because this is while, we will start with a place marker for label 1, and then we test the statement. Test if y is bigger than 5, and if it is, go to L2, and if it's not, jump to L3. And then we need to specify where do we start L2, so we put in a place marker called label L2, and we write the statement. Because the statement is y equals to y minus 1, we need to finish y minus 1 statement first. So sub y with 1 and put it into a temporary space 1, and then move t1 to y, and because this is a while statement, we want to jump back into L1 to check whether the condition is still true, and then we need to specify our exit statement. Okay, so this was how we did our translation exercise in topic 2. Starting from topic 4, this particular topic, we will be discussing translation into atom again. However, the logic that we're going to use here is a little bit different. Instead of going to L2 if the condition is true, we will only go to L2 if the condition is false. Therefore, our atoms statement will look like this. So label L1, and then we test y 5, and if the statement is false, go to L2, and then if the statement is correct, you keep on executing. Therefore, we will put in our statement here. So it's going to be sub y1 t1 move t1 to y and jump L1. Next, we specify our exit statement, which is L2. Here you can see, even though the logic is different, for this one, we jump if the statement is true to L2. Then we need to specify where L2 starts. But if the statement is incorrect, we ask it to jump to L3, where L3 is the exit statement. However, here we jump if the statement is false. If the statement is correct, we continue executing and we specify the exit statement. So if you look at the statement in blue, the number of lines that we use is a little bit reduced as compared to the statement in black. And the number of labels used is also lesser. The statement on the left used 3 labels and the statement on the right used 2 labels. Therefore, the logic that we will be using for this topic using the Decaf grammar is this logic. We jump only if the statement is false. Okay, now I'm going to show how we can use the Decaf grammar to extract the output of control structure given a particular input in Java language. And here we do not need to remember the structure anymore. We just have to follow whatever is given in the rules of Decaf grammar. Just like I mentioned previously, it is possible to extract the atoms from this particular Java statement just by looking at the Decaf grammar. So if you notice, this Decaf grammar has some new rules as addition, and these new rules are for handling control structure. So you have the rule for statement, while statement, if statement, the else part for if statement, and we have optional assign expression, optional boolean expression, and of course compound statement and statement list. And these two rules usually are not really used. The one that are more important are the individual rules for the control structure. And now I'm going to show you how we can extract the atom for this input by referring to our Decaf grammar. So the first thing that we're going to do is we're going to look at the rule for while statement. So this is the rule for while statement. And what is most important is to highlight the atoms from the while statement. So in this while statement, we have several atoms. We have label, we have jump, and we have another label. And then we have Boolean expression. You need to remember, inside Boolean expression, there is an atom. That atom is a test atom. Since while involve a comparison of Boolean expression, we also need to refer to the Boolean expression rule. And the Boolean expression rule has test atoms. Now, let's look at how I'm going to use these two rules and extract the atoms for the while input statement. So first of all, the first atom that we meet is label, and it states here is label L1. So I'm just going to follow the numbering of the labels. And then there is a Boolean expression. Then you need to remember the Boolean expression is actually handling referring to an atom, and that atom is test atom. Therefore, it's going to be test. Okay, our P is Y, our Q is 5, so Y 5. I am basically just writing down the attributes as listed in the grammar. And then 7 minus C. Since we are handling a bigger than operation, the C is 3. So I am looking at the comparison code table. 7 minus 3 is 4. And then instead of following label 1 here, I'm going to follow the label from the while statement rule. So the label here is label 2. So I'm going to follow with L2. And then statement. So this is our statement. For the statement, we're going to translate it as usual. So this is sub y1 t1, and then move t1 to y. Okay, done. And then we made another atom which is jump L1. So I'm going to follow jump L1. And finally, another atom label L2. Label L2, and we are done. So if you notice, I'm going to compare the output that we get from Decaf grammar A and the output that we get based on memorizing the structure B. So this is basically the same output, just that um, instead of y bigger than 5, we write it directly here. We write it in the form of comparison code. And the difference here, for decaf grammar, you do not need to remember the structure because decaf grammar will be given in your test and final assessment. As long as you know how to use or how to extract the atoms from the decaf grammar, you will be able to translate any control structure into its atom form. Now I am going to show how we can handle control structure that has another control structure as part of its statement. So if you look at the statement on the screen, we have a for control structure statement, and inside of it we have an if statement. So in order for us to handle this, first of all, we need to look at the rules for statement and the rules for if statement. So here is the rule for statement, and then labels involved for statement is label 1, label 2, label 3, and label 4. So if you notice here, the number of labels, we have 4. Therefore, we have L1, L2, L3, and L4. Now, as for if statement, we have label 1 and we also have label 2. So for if, we have L1 and L2. But since if is the statement for 4 and 4 already use 1 until 4, label 1 for if is going to be label 5, and label 2 for if is going to be label 6. So I'm going to demonstrate what's the atoms for this statement is going to be like. So we start with the rule for 4, and we have optional assigned expression. So optional assigned expression, if you look here, is derived to assigned expression, and assigned expression is derived to this statement, and we have an atom. For writing the atoms for an input statement, whenever we have atom inside the rule, we need to write it out. So this is basically move. Okay, so this is Q and this is P. Therefore, 0, comma, A. And then this is done. Next, we have label L1. So label L1. So this is done. And then we have optional Boolean expression. So this is not optional. We are basically looking at this statement. So optional Boolean expression is derived to Boolean expression, and Boolean expression has an atom inside of it. So this is P and this is Q. Therefore, it's going to be test A 5 7 minus C. So lesser than the comparison code is 2. So 7 minus 2 is 5. And we need to follow the label here. So if you can see, I am highlighting label here in the optional Boolean expression. The label there, the label stated there is label 4. Therefore, I'm going to follow. So this will be L4. So this is done. Next, jump L2. I'm just going to follow it directly. Jump L2. This is done. Label L3. Label L3. So this is done. Then we have optional assign expression. This is not really optional. This is actually talking about this, because you have to remember A++ is actually A equals to A plus 1. So you need to handle A plus 1 first, then you will assign it to A. This is what the assign expression is about. Therefore, I'm going to do the addition operation first. Add A1 D1, and then I have move D1 A. So this is the optional assign expression is about, which is obviously not optional. So this is done. Then we have jump L1. So following it directly, jump L1. And then we have label L2. So label L2. Next we have, so this is done. Next we have statement. So statement for 4 is referring to this, which is if statement. So starting from here, we need to look at rules concerning if. So that rule is this rule. Okay, so we start with Boolean expression, and you have to remember in Boolean expression there is a test atom where this is our P and this is our Q. So I'm going to write the statement for the atom statement for if using a different color. So I'm going to use purple. So it's going to be test. Oh, purple is not that distinctive, so I'm going to use orange. Test Y 5, and then our Boolean operator is not equal. So not equal, the comparison code is 6. So 7 minus 6 is 1. And here, for the if statement, the label is label 1. However, label 1 has been changed to L5 since if is the statement for 4. So here, instead of writing L1, I'm going to write L5. Okay, done. For this, next we have statement. The statement for if is y equals to y minus 1. So just write it directly. Sub y1 t2. Why am I using t2? Because we already used t1 here. So move t2 y. Okay, so we are done with statement, and then jump L2. I have to remember L2 for if is L6. So just directly follow jump L6. Next, we have label L1, and label L1 is L5 for if. Therefore, label L5. Okay, this is done. And then we have label L2, and L2 is L6 for if. Label L6. So we are done with if. But are we completely done? Not yet. Since just now we stopped here. We were doing the statement for 4, and we still have another 2 atoms. And the atoms are jump L3. Since we are back at 4, we can just follow the labeling of 4 rule. So we write jump L3. Oops. Jump L3. Okay, this is done. And finally, label L4. Label L4. And we are done. So this is how you derive the atoms for nested control structure, where inside the statement of one control structure is another control structure. So this is the input and this is the output in the form of atoms.